Problem 5.5 from the book Make One Candidate Stop. So here is the statements. Before discussing the statement, I will let you know what is Otto cycles, how many processes are there, and its explanations. Each process, what each process basically describe on a PV diagram. So let me draw the Otto cycle. So this is the PV diagram of the Otto cycle. You know that Otto cycle have two constant volume process and two isentropic processes. So it means that we have one constant volume cycle. Constant volume process means that the volume at such process is constant. So if I consider this as a one point, this is the second point. So the volume at the both the points is the same. Next is the another constant volume process, and this is isentropic expansion process. Okay, and this is the isentropic compression process. Let me explain it. So if I consider this as a state point 1, so 1 up to 2 is called isentropic compression. Isentropic compression. Why isentropic compression? Because in compressions volume is gradually decreasing and the pressure is increasing, so the same process has been taken place here. So the pressure at P2 is higher as compared to pressure at P1, and volume at V1 is maximum as volume at V2 is less because compression has been taken place. Now from 2 to 3 there is heat addition process, that is Qn. Okay, and 3 to 4 is expansion process. Here the expansion, so that will provide the power output to you, work output. 3 to 4 is also isentropic expansion process. Here it is isentropic expansion process. And then 4 to 1 is mm, Q out. Q out means exhaust. So the Otto cycle, remember, works on the petrol engine. So for process 4 to 1, here is the Q out will take place. So the heat rejection will take place. So you can say the exhaust process 4 to 1. Now come to the, so let me explain one more thing. So the maximum temperature will obtain at a temperature at a point T3 because heat addition is taken place. So after heat addition, maximum process in the cycle is obtained, that is at a point 3, and minimum temperatures, so after heat rejection, is obtained at a T1. Okay. Now come to the statement. In an air standard Otto cycle, the maximum and minimum temperature are 1400 and 15 centigrade. So it means that the maximum, as I earlier discussed, that maximum temperature is T3, that is 1400 centigrade. So if you convert that into Kelvin, just add 273 with this value, it will become 1673 Kelvin. Next is to the minimum temperature. The minimum temperature is at a T1, so the T1 is equal to 15 centigrade. So if you convert that into Kelvin, then T1 is equal to 288 Kelvin. So just simply add 273, this is 15 centigrade, you will convert that into Kelvin. The next thing is the heat supplied per kilogram of air is 800 kilojoules. So the heat that is supplied from process 2 to 3 is Qn. That is Qn is 800 kilojoule per kg. Okay. Now what we have to calculate? Calculate the compression ratio. So we have to calculate the compression ratio is denoted by RV, compression ratio, and the cycle efficiency. So here I already written the cycle efficiency. Calculate also the ratio of maximum to minimum pressures in the cycle. So if I draw the PV diagram here, if you look at here, the maximum pressure you will get at P3. So the ratio of sorry, P3 divided by the minimum pressure that is at P1. So that is P1 we need to calculate. Okay. So these three data we are need to calculate in this problem. Statements of efficiency, compression ratio, and the ratio between maximum and minimum pressure of the cycle. Let's begin its solution. The heat that is supplied from process 2 to 3 is equal to Cv into T3 minus T2. Here the Qn that is supplied is 800 kilojoule, and what is Cv? Cv value of air is 0.718, 1673, and T2 is need to calculate. So after doing simplification, so if you divide this 0.718 with both sides, you will get, finally if you do the simplification, you will get the T2 value, that is 558.8 Kelvin. So this is the T2 value. The maximum temperature, that is T3, has been given, and the T2, that is the T2 temperature. Now we calculated from this equation where heat is supplied. At the temperature at T2 and T1 is has been calculated. So at the temperature, minimum temperature T1 is given and T2 has been calculated from this equation. So now if we apply the isentropic equations that correlate between temperature and volumes, then we can find the compression ratio, because the compression ratio is equal to maximum volume divided by minimum volume of the system or the cycle, you can say. So before that, we know that V1 divided by V2, that is equal to, so gamma minus 1, that is equal to T2 divided by T1. So we are interested to find this value. Put the values of calculated here, 558.8 divided by T1, that is 288. And you shift this from there to that side. The value of V1 divided by V2 is 558.8 divided by 288. So after doing the simplification, so if you divide 1 divided by 0.5, you will get 2.5. So after doing these calculations on calculators, you will find the compression ratio is 5.243. So the compression ratio is equal to the maximum volume to the minimum volume, and that is equal to 5.243. So the compression ratio you will get, that is 5.243. So this is the one answer that is required to calculate in the statement has been calculated. Efficiency of this cycle, so efficiency of the Otto cycle is 1 minus 1 over RV. RV is the compression ratio, gamma minus 1 into gamma minus 1. So simply just put the values in, and doing the simplification you will get its value. So the RV value is 5.243 into gamma. Gamma is 1.4. If you subtract 1, it will become 0.4. So after solving it on calculator, you will get an efficiency, that is 48.4%. So this is the second part of this problem, that is our requirement. Now the third part we are to evaluate now the third part of this problem to find the maximum minimum pressure ratio of the cycle. So P2 divided by P1 is equal to T2 divided by T1. So an isentropic process P2 divided by P1 correlate with T2 divided by T1 if there is gamma minus 1 divided by gamma. Okay. So if you are interested to find the P2 divided by P1, so we need to eliminate these terms and convert that into that side. So that P2 divided by P1 will become T2 divided by T1 and it becomes gamma divided by gamma minus 1. Now just simply put the corresponding value. What is T2? That is 558.8 and T1 value is 288 and gamma is 1.4 divided by 0.4. So after doing uh, calculations you will get the P2 divided by P1 value, that is almost 10.175. 10.175. Let's say we call it equation A. Okay, next is to find the pressure ratio of, so let me come here. So the pressure ratio of P2 to P1 has been calculated with the help of the isentropic formulas applications. Now from process P2 to P3 there is a constant volume process, so there is a direct relationship between pressures and temperature. So here I can write that P3 divided by P2 is equal to T3 divided by T2. There is a direct relationship which volume is constant, so the pressures and temperatures have direct relation. No exponent is required. So P3 divided by P2, that is equal to, what is T3 value? T3 value is maximum temperature value, that is 1673 divided by T2 is 558.8. So after doing simplifications you will get P3 divided by P2, that is 2.994. 2.994 equation B. P3 divided P1 value, find the P3 divided P1 value, multiply equation A and B with each others and each side with A with the corresponding side. So the P3 divided by P2 multiply by P2 divided by P1 is equal to, so this side term is equal to 2.944 multiplied by 10.175. So this P2 will be cancelled out with this. So the ratio, so the maximum pressure ratio to the minimum pressure ratio you will get, that is 30.46. So the maximum to minimum pressure ratio of the cycle of 10 is 30.463. And because the maximum pressure you will get at the point P3, as I already mentioned there, and the minimum pressure you will get at the point P1, and their corresponding ratio will be 30.46. Thank you so much for watching this problem 5.5 from the book Megonki. More such videos are coming soon. Stay tuned with us.